Welcome, traveler. I activate my balm of stars to soothe your rest and guide your learning. Let us begin the journey. Imagine the universe as a grand, cosmic ocean. We've spent centuries charting the visible currents, the stars, planets, galaxies, the things we can see with our telescopes. But beneath those visible currents lies a deeper, more subtle realm. A realm populated by particles that rarely interact with matter, yet are unbelievably abundant. These are neutrinos. They're not just another particle. They represent a fundamental gap in our understanding of the universe. Why dedicate an entire course to them? Because neutrinos hold keys to some of the biggest unsolved mysteries in physics. They could explain the imbalance between matter and antimatter, why there's something rather than nothing, and provide insights into the very birth of the universe. Their elusive nature forces us to refine our theories, to push the boundaries of our knowledge, and to develop incredibly innovative detection methods. It's a humbling pursuit, constantly reminding us just how much we don't know. Think of the standard model of particle physics as a comprehensive map of all known fundamental particles and the forces governing their interactions. It's incredibly successful, predicting countless experimental results with astounding accuracy. But it's incomplete. For decades, the standard model couldn't account for neutrino mass. Initially, it predicted neutrinos were massless, like photons. However, experiments consistently showed that neutrinos do have mass, albeit incredibly tiny. This discovery was revolutionary, proving the standard model needed modification. Furthermore, observations of neutrinos from distant supernovae provided evidence that the standard model's description of neutrino oscillations, the changing flavor of a neutrino as it travels, was also incomplete. These anomalies aren't minor adjustments. They point to physics beyond the standard model. Neutrinos, therefore, are not simply another piece of the puzzle, but a beacon guiding us towards a more complete understanding of reality. The study of neutrinos isn't just about abstract theoretical physics. It has real-world implications. Understanding neutrino interactions is crucial for designing future neutron reactors and for monitoring them for safety and security. Neutrinos are produced in abundance during nuclear fission, so accurately modeling their behavior is essential for reactor design. Moreover, studying neutrinos can help us understand the processes occurring within stars, providing insights into stellar evolution and nucleosynthesis, how elements are created in the universe. Even more tantalizingly, some theoretical models suggest that neutrinos may play a role in the formation of heavy elements in supernovae, potentially explaining the abundance of elements heavier than iron. In essence, by unraveling the mysteries of neutrinos, we're gaining a deeper understanding of the universe's past, present, and future, and our place within it. Over the next 13 chapters, we'll embark on a journey to understand the fascinating world of neutrinos. We'll start with the basics, the different types of neutrinos, their properties, and how they interact with matter. We'll delve into the history of neutrino physics, tracing the key experiments and discoveries that have shaped our understanding. Then we'll move on to more advanced topics, such as neutrino oscillations, neutrino mass, and the search for sterile neutrinos. We'll explore the theoretical models that attempt to explain these phenomena, and we'll examine the experimental challenges involved in detecting these elusive particles. This isn't going to be a purely theoretical course. We'll also explore the technologies used to detect neutrinos, from massive underground detectors filled with thousands of tons of water or mineral oil, to sophisticated experiments using nuclear reactors and particle accelerators. The goal is not simply to learn about neutrinos, but to develop a deep intuition for their behavior, and to appreciate the scientific process involved in unraveling their mysteries. Each chapter will build upon the previous one, gradually increasing in complexity. We'll start with the fundamentals and then move on to more advanced concepts. I'll be presenting the material in a clear and concise manner, using analogies and examples to help you grasp the key ideas. We'll also be looking at some of the current research being conducted in the field, exploring the latest discoveries and the open questions that remain. Throughout the course, I'll encourage you to think critically and to challenge your assumptions. Science isn't about memorizing facts, it's about asking questions, designing experiments, and interpreting data. I want you to become an active participant in the learning process, not just a passive recipient of information. This course assumes a basic understanding of introductory physics, particularly mechanics, electromagnetism, and quantum mechanics. However, I'll be providing plenty of background information and explanations along the way, so don't worry if you're a little rusty on some of the basics. By the end of this course, you'll have a solid understanding of neutrino physics, from the basics to the cutting-edge research. You'll be able to explain the different types of neutrinos, their properties, and how they interact with matter. You'll understand the experimental evidence for neutrino oscillations and neutrino mass. You'll be familiar with the theoretical models that attempt to explain these phenomena, and you'll appreciate the challenges and opportunities involved in the search for new physics beyond the standard model. More importantly, you'll have developed the critical thinking skills and the scientific intuition needed to tackle any complex scientific problem. This course isn't just about learning what we know about neutrinos. It's about learning how we know it and how we can continue to push the boundaries of our knowledge. So, let's begin our exploration of these elusive, yet profoundly important, ghost particles. The standard model of particle physics is, in many ways, a triumph of human intellect. It's a remarkably successful theory that describes the fundamental constituents of matter and the forces that govern their interactions. It categorizes particles into two main types: fermions, which are the building blocks of matter, like quarks and leptons, and bosons, which mediate the forces between them, like photons and gluons. The leptons include the familiar electron and muon, as well as the heavier type particle and the corresponding neutrinos, the electron neutrino, muon neutrino, and tau neutrino. For decades, the standard model has accurately predicted the results of countless experiments, solidifying its place as the cornerstone of modern physics. However, despite its successes, the standard model is not a complete theory. It leaves several fundamental questions unanswered, and it fails to explain certain observed phenomena. Think of it as a beautifully crafted map of a vast continent, but with significant portions still uncharted. One of the biggest missing pieces is gravity. The standard model doesn't incorporate gravity, which is described by Einstein's theory of general relativity. Reconciling general relativity with quantum mechanics, the framework underlying the standard model, remains one of the biggest challenges in modern physics. Another issue is the existence of dark matter and dark energy, which make up the vast majority of the universe's mass-energy content, but don't interact with light, making them invisible to our telescopes. The standard model has no explanation for these mysterious substances. Furthermore, the standard model predicts that the masses of neutrinos should be zero, but experiments have shown that they have a tiny but non-zero mass. This discrepancy requires an extension to the standard model. And, as we've already discussed, the standard model fails to explain the matter-antimatter asymmetry. Why there's so much more matter than antimatter in the universe. All these gaps point to the existence of physics beyond the standard model, and neutrinos, with their unusual properties, are proving to be a crucial window into this new physics. The search for physics beyond the standard model involves a variety of approaches, including high-energy collider experiments like those at the Large Hadron Collider, and astrophysical observations. But neutrino physics offers a unique and complementary avenue of investigation. Because neutrinos interact so weakly with matter, they can travel vast distances without being absorbed or deflected. This allows us to probe the universe in ways that are impossible with other particles. Furthermore, the unusual properties of neutrinos, their tiny mass, their ability to oscillate between different flavors, and their potential role in the matter-antimatter asymmetry suggests that they may be connected to new particles and forces that lie beyond the standard model. By studying neutrinos in detail, we can hope to uncover the secrets of these new particles and forces, and to build a more complete and accurate picture of the universe. Neutrinos, therefore, are not simply another piece of the puzzle. They are a beacon guiding us towards a deeper understanding of reality. Let's begin with a fundamental concept: lepton number. Now, you're likely familiar with conservation laws. Energy is conserved, momentum is conserved. These laws are cornerstones of physics. Lepton number is another one of these conserved quantities. But what is a lepton? Well, electrons are leptons. Muons and taus are also leptons, heavier cousins of the electron. And, crucially, neutrinos are leptons too. Every lepton has a corresponding lepton number. We arbitrarily assign electrons, muons, and taus a lepton number of 1. They're antiparticles. Positrons, antimuons, and antitaus get a lepton number of -1. Neutrinos and antineutrinos also follow this convention. 1 for the neutrino, -1 for the antineutrino. The principle of lepton number conservation simply states that the total lepton number in a closed system remains constant. This means leptons can be created or destroyed, but always in a way that the overall lepton number doesn't change. For example, a neutron can decay into a proton, an electron, and an antineutrino. The initial lepton number 0 equals the final lepton number 0, 1 from the electron, -1 from the antineutrino. This conservation law isn't just a mathematical trick. It's been experimentally verified countless times and is vital in understanding particle interactions. Now let's explore how lepton number conservation plays out in real particle interactions. Consider beta decay, a common radioactive process. A neutron within an unstable nucleus transforms into a proton, an electron, and an antineutrino. Before the decay, the system has a neutron lepton number 0, and a proton also 0. After the decay, we have a proton 0, an electron 1, and an antineutrino -1. The total lepton number remains 0. This isn't just a neat accounting trick, it's a powerful constraint on how particles interact. It tells us that certain decays are simply impossible if they would violate lepton number conservation. Another important example is the creation of particle-antiparticle pairs. If a high-energy photon interacts with a nucleus, it can create an electron-positron pair. This process conserves lepton number because the electron has 1 and the positron has -1, resulting in a net lepton number of 0. Understanding lepton number of 0. Understanding lepton number of 0. Understanding lepton number conservation is crucial because it connects seemingly disparate processes and helps us build a consistent picture of the subatomic world. It's a testament to the underlying symmetries of nature. It's important to remember that lepton number conservation isn't a perfect law in all scenarios. There have been theoretical suggestions and ongoing experiments searching for what's called lepton number violation. These scenarios involve phenomena like neutrinos double beta decay, where two neutrons decay into two protons, two positrons, and no neutrinos. If observed, this would prove that lepton number isn't actually conserved and would have profound implications for our understanding of particle physics, potentially hinting at new physics beyond the standard model. However, despite decades of searching, neutrinoless double beta decay remains elusive. The fact that we haven't observed lepton number violations so far doesn't mean it doesn't exist, only that it's incredibly rare, or that the conditions required for it to occur are extremely specific. The search for lepton number violation remains an active and exciting area of research, pushing the boundaries of our knowledge and challenging our assumptions about the fundamental laws of nature. And this constant refinement, this questioning of established truths, is the very heart of scientific progress. Now let's move on to the properties of the neutrino itself. One of the most defining characteristics of the neutrino is its lack of electric charge. Unlike electrons, which carry a negative charge, neutrinos are electrically neutral. This neutrality is a key reason why neutrinos interact so weakly with matter. Because they have no charge, they don't experience the electromagnetic force, which governs interactions between charged particles. This is why neutrinos can pass through vast amounts of matter, even entire planets, with very little chance of interacting. It's like trying to catch a ghost that's simply not built to be caught by the things we use to catch other particles. This weak interaction is both a blessing and a curse for scientists. It makes neutrinos incredibly difficult to detect, requiring massive detectors and years of data collection. But it also makes them unique probes of the universe, allowing us to study processes that would be opaque to charged particles. Next, let's talk about spin. Spin is an intrinsic form of angular momentum that all particles possess. It's not literally the particle spinning, but rather an inherent property that dictates how it behaves in magnetic fields and interactions. Particles can have integer spin 0, 1, 2, or half integer spin 12, 32, 52. Particles with integer spin are called bosons, while those with half integer spin are called fermions. Neutrinos are fermions, specifically spin 12 particles. This means that they obey the Pauli exclusion principle, which states that no two identical fermions can occupy the same quantum state simultaneously. This principle is crucial for understanding the structure of matter and the behavior of electrons in atoms. Spin of the neutrino also plays a role in how it interacts with other particles. For example, the direction of the neutrino spin can affect the probability of certain interactions occurring. Understanding the spin of the neutrino is essential for building accurate models of particle interactions and for interpreting experimental data. The combination of zero charge and spin 12 makes the neutrino quite unique. It's one of the most elementary particles we know, and its properties are profoundly different from those of other particles like electrons or protons. Because it doesn't interact through the electromagnetic or strong force, the neutrino only interacts via the weak force and gravity. The weak force is, as the name suggests, incredibly weak, which is why neutrinos are so difficult to detect. Furthermore, the weak force is chiral, meaning it distinguishes between left-handed and right-handed neutrinos. This chirality has important implications for our understanding of neutrino oscillations, which we'll discuss later. The combination of these properties, zero charge, spin 12, weak interaction, and chirality, makes the neutrino a truly fascinating and mysterious particle, and continues to drive ongoing research in particle physics. Now, let's address the long-standing question. Do neutrinos have mass? For a long time, it was assumed that neutrinos were massless, a consequence of the simplest versions of the standard model of particle physics. However, experiments in the late 20th and early 21st centuries provided compelling evidence that neutrinos do indeed have mass, albeit a very, very small mass. The key evidence came from observations of neutrino oscillations. Neutrino oscillations are a quantum mechanical phenomenon where neutrinos change flavor. That is, they change from one type electron neutrino, muon neutrino, tau neutrino into another as they travel. If neutrinos were massless, they wouldn't be able to oscillate. The oscillation requires that neutrinos have a non-zero mass, allowing them to mix and change flavor. The first direct evidence of neutrino oscillations came from experiments studying neutrinos produced by cosmic rays interacting with the atmosphere. These experiments observed a deficit of muon neutrinos arriving at detectors on Earth, compared to the number expected based on the initial production rate. This deficit could only be explained if some of the muon neutrinos had oscillated into other flavors, such as tau neutrinos. Subsequent experiments using neutrinos produced by nuclear reactors and particle accelerators confirmed these findings and provided further evidence for neutrino oscillations. These experiments allowed us to measure the differences in the squares of the neutrino masses, which are denoted as M12 and M23. However, we still don't know the absolute values of the neutrino masses. We only know the differences between them. Determining these absolute masses remains one of the biggest challenges in neutrino physics. The fact that neutrinos have mass has profound implications for our understanding of the universe. It suggests that the standard model of particle physics is incomplete, and that there is new physics beyond it. The tiny mass of the neutrino also plays a role in cosmology, affecting the formation of large-scale structures in the universe. Furthermore, the observation of neutrino mass opens up the possibility of the neutrino being a Majorana particle, meaning it is its own antiparticle. This is a highly speculative idea, but it has important implications for our understanding of matter and the origin of the universe. The search for the absolute mass of the neutrino and the investigation of its properties continue to be active areas of research, pushing the boundaries of our knowledge and challenging our fundamental understanding of the universe. We've established that neutrinos are elusive particles, famously interacting very weakly with matter. But what we didn't cover is that they aren't all the same. When we first detected neutrinos, we assumed there was just one type. However, over time, experiments revealed that there are actually three flavors of neutrinos: the electron neutrino, the muon neutrino, and the tau neutrino. Think of flavors not as tastes, but as different kinds of neutrinos, each associated with a charged lepton. The electron, muon, and tau, respectively. Each of these leptons is a fundamental particle, much like the electron, but heavier and less stable. The electron neutrino is the lightest and most common, created in processes like nuclear fusion in the Sun. The muon and tau neutrinos are heavier and created in higher energy environments, like cosmic ray interactions or particle accelerators. It's important to remember that these flavors aren't intrinsic properties like mass or charge. They're more like labels describing how the neutrino interacts with matter, and which charged lepton it's most likely to become associated with when it interacts. Detecting the different flavors isn't straightforward. A neutrino doesn't announce its flavor. Instead, scientists infer the flavor based on the particle that's produced when the neutrino interacts. For example, if a neutrino collides with a neutron in a detector and produces an electron, we identify it as an electron neutrino. Similarly, detecting a muon indicates a muon neutrino, and a tau particle signals a tau neutrino. This process relies on the fact that neutrinos, despite being flavor-changing, are always associated with one of these charged leptons upon interaction. Early experiments focused on detecting electron neutrinos from the Sun, as they're produced in abundance through nuclear fusion. However, discovering muon and tau neutrinos required more sophisticated detectors and high-energy sources, like particle accelerators, as these flavors are less common in natural processes. These experiments validated the existence of all three neutrino flavors, confirming our understanding of the Standard Model though. As we'll see, the story doesn't end there. It's crucial to understand that these flavors aren't fixed. A neutrino born and known as an electron neutrino doesn't remain an electron neutrino forever. This brings us to the most fascinating and perplexing aspect of neutrino behavior: flavor oscillation. For decades, there was a major problem with our understanding of neutrinos. Experiments measuring the number of electron neutrinos arriving from the Sun were consistently lower than predicted by the Standard Model and our understanding of solar fusion. This was known as the solar neutrino problem. Many explanations were proposed, but the correct one turned out to be far more radical than anyone anticipated. Neutrinos were changing flavors as they traveled. This means that an electron neutrino born in the Sun could transform into a muon neutrino or a tau neutrino before reaching our detectors on Earth. This isn't a simple case of mixing. It's a quantum mechanical phenomenon where the neutrino exists as a superposition of all three flavors simultaneously, and the probabilities of measuring each flavor change over time and distance. To understand flavor oscillation, we need to think about neutrinos not as definite particles with fixed flavors, but as quantum mechanical states. Each neutrino flavor, electron, muon, and tau, can be represented as a combination of three neutrino mass states. These are the states with definite mass, but indefinite flavor. The flavor states are therefore superpositions of these mass states. When a neutrino is created, it's born in a specific flavor state, but as it travels, the mass states within that superposition evolve at different rates. This difference in evolution causes the probabilities of measuring each flavor to change over time and distance. Imagine three waves traveling together, each with a slightly different frequency. Over time, their interference pattern will change, creating areas of constructive and destructive interference. Neutrino oscillation is similar. The probabilities of measuring each flavor oscillate as the neutrino travels, due to the interference of the mass states. The frequency of these oscillations depends on the differences in mass between the mass states and the distance traveled. The discovery of neutrino oscillation was a groundbreaking achievement, and it required extremely sensitive detectors and long baseline experiments. These experiments involved creating a beam of neutrinos at one location and detecting them at a distant location, often hundreds of kilometers away. By measuring the number of neutrinos of each flavor at the source and at the detector, scientists can determine how the flavors have changed over the distance traveled. The Super Kamiokande detector in Japan and the Daya Bay reactor neutrino experiment in China are prime examples of these experiments. They have precisely measured the oscillation parameters, the differences in mass squared between the mass states, and the mixing angles that determine the probabilities of transitioning between flavors. The fact that neutrinos oscillate proves that they have mass, even though the standard model originally predicted them to be massless. This discovery required an extension to the standard model and opened up new avenues of research in particle physics. The implications of neutrino oscillation extend far beyond particle physics. The mass of neutrinos, though incredibly small, affect the large-scale structure of the universe. The total mass of all neutrinos in the universe contributes to the overall density of matter, influencing the expansion rate and the formation of galaxies. Furthermore, the fact that neutrinos have mass suggests that there might be new physics beyond the standard model, such as sterile neutrinos, hypothetical particles that don't interact with matter through the weak force. The study of neutrino oscillation is therefore a window into the fundamental nature of the universe, and it continues to be a vibrant area of research for physicists around the world. The ongoing and future neutrino experiments, such as the Deep Underground Neutrino Experiment DUNE, will provide even more precise measurements of the oscillation parameters and will search for new phenomena, such as CP violation in the lepton sector potential asymmetry between matter and antimatter. To describe the probability amplitudes of neutrino flavor transitions mathematically, physicists use the Pontecorvo-Maki-Nakagawa-Sakata PMNS matrix. This is a 3x3 unitary matrix that, analogous to the Kabibo-Kobayashi-Maskawa CKM matrix for quarks, describes the mixing between the flavor eigenstates and the mass eigenstates of neutrinos. The elements of the PMNS matrix determine the probabilities of a neutrino of one flavor transforming into another flavor as it travels. Understanding these mixing angles and phases is crucial to understanding neutrino oscillation. The matrix can be parameterized by 3 mixing angles, 12, 13, and 23, and 1 CP violating phase. These parameters encode the information needed to predict the oscillation probabilities for any given neutrino energy and distance. Precise measurements of these parameters are a major goal of current and future neutrino experiments. Current experimental data has allowed us to determine the values of 2 of the mixing angles, 12 and 13, with relatively high precision. 12 is known to be around 33.8 degrees, and 13 is around 8.8 degrees. These values indicate that the mixing between the neutrino flavors is significant, but not maximal. The value of 23 is still less well known, but it is believed to be close to 45 degrees, which would imply maximal mixing. Determining the value of 23 with higher precision is a major goal of ongoing experiments. The CP violating phase is also currently unconstrained, and determining its value would be crucial to understanding the matter-antimatter asymmetry in the universe. CP violation in the lepton sector, if observed, could provide insights into the fundamental symmetries of nature and potentially explain why there is more matter than antimatter in the universe. The PMNS matrix, along with the PMNS matrix, provides a powerful framework for understanding neutrino mixing and oscillation. However, it's important to remember that this is just a description of the observed phenomenon, not an explanation. The underlying physics that drives neutrino mixing is still unknown. One possibility is that neutrinos mix due to interactions with new particles or forces beyond the standard model. Another possibility is that the PMNS matrix is not a fundamental parameter, but rather an emergent property of some deeper theory. Ongoing and future neutrino experiments will continue to probe the mysteries of neutrino mixing and oscillation, providing new insights into the fundamental nature of the universe and potentially revolutionizing our understanding of particle physics. Our journey to understand neutrinos truly begins with their most abundant source, the Sun. It's almost counterintuitive, isn't it? These incredibly elusive particles are produced in vast quantities within the nuclear furnace at the Sun's core. To grasp how, we need to briefly revisit nuclear fusion. The Sun doesn't burn like wood or coal. It's powered by a different process, a merging of atomic nuclei, specifically hydrogen nuclei, under immense pressure and temperature around 15 million degrees Celsius. This fusion creates helium and, crucially, releases a tremendous amount of energy that sustains life on Earth. But it also generates neutrinos. Specifically, these are electron neutrinos, born directly from the beta decay processes occurring during the proton-proton chain and the CNO cycle, both pathways to helium production. Each fusion event doesn't just release photons, light and heat, but also a neutrino, which carries away a tiny portion of the energy. These neutrinos, however, don't interact strongly with matter, allowing them to escape the Sun's core almost unimpeded. This is why so many reach Earth, and why detecting them is so challenging. The sheer number of solar neutrinos reaching Earth is staggering. Every second, approximately 65 billion solar neutrinos pass through every square centimeter of your body. That's an incomprehensible number. Yet, for decades, experiments designed to detect them consistently measured significantly fewer neutrinos than predicted by our standard solar model, the prevailing theory of how the Sun works. This discrepancy became known as the solar neutrino problem. It wasn't a problem with the Sun. It was a problem with our understanding of neutrinos themselves. The initial experiments, like the Homestake experiment and Kame-Kandi, were designed to detect only electron neutrinos. What we later discovered through experiments like Super Kame-Kandi and SNIB Sudbury Neutrino Observatory is that neutrinos have mass, and they oscillate, meaning they change flavor as they travel. An electron neutrino born in the Sun can transform into a muon neutrino or a tau neutrino on its journey to Earth. Those early experiments weren't detecting all the neutrinos because they weren't looking for the missing flavors. The resolution of the solar neutrino problem provided crucial evidence for neutrino mass and oscillations, a major step forward in particle physics. The implications of neutrino oscillation are profound. It tells us the standard model of particle physics, while incredibly successful, is incomplete. It requires an extension to accommodate massive neutrinos. And while we now have a good understanding of the mechanism behind the solar neutrino deficit, it also highlights the difficulty of studying these elusive particles. Detecting neutrinos requires massive detectors, often located deep underground, to shield them from other forms of radiation. These detectors aren't looking for the neutrinos directly, but rather for the rare instances when a neutrino interacts with an atom within the detector, producing a detectable signal, a flash of light, or a charged particle. It's like trying to catch snowflakes in a hurricane. Unlike solar neutrinos, which originate from a specific fusion process, atmospheric neutrinos are created in a much more chaotic manner. They're a byproduct of cosmic ray interactions with the Earth's atmosphere. Cosmic rays are high-energy particles, mostly protons and atomic nuclei, originating from outside our solar system, from sources like supernovae and active galactic nuclei. When these cosmic rays collide with atoms and molecules in the upper atmosphere, they initiate a cascade of secondary particles, including pions and kaons. These short-lived particles then decay, producing neutrinos, all three flavors: electron, muon, and tau neutrinos. The creation of atmospheric neutrinos is quite democratic. Roughly equal amounts of all three flavors are produced at the initial interaction. The flux or rate of atmospheric neutrinos depends on several factors, including the energy of the primary cosmic rays, the altitude, and the latitude. Higher altitudes generally receive more cosmic rays, and the flux is also higher at lower latitudes due to the Earth's magnetic field deflecting some of the charged cosmic rays. However, the most interesting aspect of atmospheric neutrinos is that they exhibit a significant degree of oscillation, even more pronounced than solar neutrinos. This is because atmospheric neutrinos travel much longer distances through the Earth, sometimes traversing the entire planet before reaching a detector. This extended path length enhances the probability of oscillation, allowing scientists to study the parameters governing this phenomena in detail. Detecting atmospheric neutrinos requires detectors with immense volume and sophisticated capabilities. IceCube, located at the South Pole, is a prime example. It uses a cubic kilometer of Antarctic ice as its detector medium, instrumented with thousands of optical sensors to detect the faint Cherenkov radiation emitted when a neutrino interacts with an ice molecule. By analyzing the direction and energy of the detected muons, a common product of neutrino interactions, scientists can reconstruct the trajectory of the original neutrino and pinpoint its source, providing valuable insights into the origin and composition of cosmic rays. Moving from natural sources to human-generated ones, nuclear reactors are a significant source of antineutrinos, specifically electron antineutrinos. Unlike the sun or cosmic ray interactions, the production of antineutrinos in reactors is relatively well understood. It's a direct consequence of beta decay occurring during nuclear fission, the process that generates heat in a nuclear reactor. When uranium or plutonium nucleus splits, it produces a variety of fission fragments, many of which are neutron-rich. These fragments undergo beta decay, emitting an electron and an electron antineutrino. The intensity of reactor antineutrino flux is directly proportional to the reactor's power output and the fuel composition. This predictability makes reactor antineutrinos an ideal tool for various applications, including reactor monitoring and the search for sterile neutrinos, hypothetical particles beyond the standard model. Experiments like Daya Bay and RNO have used reactor antineutrinos to precisely measure the mixing angle 13, a crucial parameter governing neutrino oscillations. These experiments utilize massive liquid scintillator detectors placed at varying distances from the reactor core to monitor the flux and energy of the antineutrinos. The use of reactor antineutrinos for remote reactor monitoring is a fascinating application. By precisely measuring the antineutrino flux, it's possible to verify the reactor's power output without physically accessing the core, enhancing safety and security. This technology is particularly relevant for verifying international safeguards and ensuring the peaceful use of nuclear energy. While the flux of reactor antineutrinos is lower compared to solar or atmospheric neutrinos, its predictability and controllability make it a valuable resource for fundamental research and practical applications. Finally, the most energetic and fortunately rare source of neutrinos are supernovae, the explosive deaths of massive stars. During the supernova, a tremendous amount of energy is released in the form of neutrinos, far more than in any other known process. Approximately 99% of the total energy released in a supernova is carried away by neutrinos, primarily electron neutrinos and electron antineutrinos, but also muon and tau neutrinos. These neutrinos are produced in a variety of processes within the collapsing star and the newly formed neutron star. Detecting supernova neutrinos is a significant challenge due to their low flux and the rarity of supernova events. Large-scale neutrino detectors like Super Kamiokande and IceCube are continuously monitoring the sky for these elusive particles. A nearby supernova, within a few kiloparsecs, would produce a burst of neutrinos that could be detected by these detectors, providing valuable insights into the physics of core collapse and the formation of neutron stars and black holes. The detection of supernova neutrinos would not only confirm our theoretical understanding of core collapse, but also provide a unique probe of the extreme conditions within the collapsing star. These neutrinos carry information about the temperature, density, and composition of the core, which is otherwise inaccessible. Moreover, supernova neutrinos are believed to play a crucial role in the synthesis of heavy elements through a process called the R process, contributing to the chemical enrichment of the universe. While we haven't yet detected a significant burst of supernova neutrinos, the search continues, promising a wealth of new discoveries in the years to come. We've spent the last few chapters discussing the incredibly elusive nature of neutrinos. They barely interact with matter, and that's the core of the challenge when it comes to detecting them. Imagine trying to catch a ghost, a literal ghost. You can't just set a net out. You need to infer its presence from the very subtle disturbances it causes. Neutrino detection isn't about directly seeing them. It's about detecting the incredibly rare instances when they do interact with matter. And because these interactions are so rare, we need massive detectors and incredibly sensitive instruments. The sheer volume of material we need to work with is astonishing. We're talking about thousands of tons of water or specialized scintillating fluids, carefully shielded from all other forms of radiation. Think about the scale. It's not a tabletop experiment. It's a significant engineering undertaking. The difficulty isn't just the rarity of interaction. It's also the fact that when a neutrino does interact, the energy deposited is often quite low. This makes it hard to distinguish a neutrino event from the background noise, the constant stream of other particles and radiation that's always present. We need to be able to filter out that noise and isolate the signal, which is like trying to hear a whisper in a hurricane. It's a truly remarkable feat of physics and engineering. Another key challenge is shielding. Because neutrinos are so weakly interacting, we need to protect our detectors from other particles that do interact strongly. Cosmic rays, for instance, are a constant bombardment from space, and they can easily mimic a neutrino signal. To block these particles, we often build our detectors deep underground, in mines or tunnels, to use the Earth itself as a shield. The deeper you go, the more material there is above you, and the fewer cosmic rays reach the detector. Think of it like digging a hole to escape the rain. It's a simple but effective principle. But even underground, there's still some background radiation to contend with. Radioactive decay in the surrounding rocks, and even in the detector materials themselves, can produce unwanted signals. So, we need to carefully select materials with low radioactivity and use additional shielding to further reduce the background noise. It's a constant battle to isolate the rare neutrino signal from all the other sources of radiation, and it requires a meticulous attention to detail and a deep understanding of all the potential sources of background noise. Finally, there's the challenge of identifying the type of neutrino. There are three flavors: electron, muon, and tau, and each one interacts in a slightly different way. Detecting an electron neutrino, for example, is different than detecting a muon neutrino. We need to design our detectors to be sensitive to all three flavors and to be able to distinguish between them. This often involves using different types of detector materials and different detection techniques. For instance, some detectors are better at detector materials. It's like having a set of specialized tools, each designed for a specific task, and it requires a careful analysis of the data to determine which flavor of neutrino caused the interaction. It's a complex and challenging process, but it's essential for understanding the properties of these mysterious particles. To recap, detecting neutrinos is incredibly difficult due to their weak interactions, the need for massive detectors, the challenges of shielding, and the difficulty of identifying the neutrino flavor. It's a testament to the ingenuity of physicists and engineers that we've been able to detect these particles at all. Now, let's talk about how we actually detect these elusive particles. One of the most important techniques relies on something called Cherenkov radiation. This is a fascinating phenomenon that occurs when a charged particle travels through a medium, like water, at a speed faster than the speed of light in that medium. Now, this doesn't violate Einstein's theory of relativity, which states that nothing can travel faster than the speed of light in a vacuum. The speed of light is slower in materials like water or glass. Imagine a boat traveling through water. It creates a wake, a V-shaped wave pattern. If the boat travels faster than the speed of the waves it creates, it outruns them and they pile up, creating a shock wave. Cherenkov radiation is the electromagnetic equivalent of that shock wave. It appears as a faint, bluish light, and it can be detected by sensitive photomultiplier tubes. The Super Kamiokande detector in Japan is a prime example of a Cherenkov detector. It's a massive tank filled with 50,000 tons of ultra-pure water, surrounded by thousands of photomultiplier tubes. When a neutrino interacts with a water molecule, it can produce a charged particle, like an electron or a muon, that travels faster than the speed of light in water, emitting Cherenkov radiation. The photomultiplier tubes detect this radiation, allowing us to reconstruct the path and energy of the charged particle, and thus infer the properties of the neutrino. The pattern of light detected by the photomultiplier tubes tells us the direction the particle was traveling, and the amount of light tells us its energy. It's like reconstructing a crime scene from the evidence left behind. The sheer size of the detector is crucial because it increases the probability of a neutrino interacting within the tank. The larger the volume, the more neutrinos we can catch. Of course, Cherenkov detectors aren't perfect. They're susceptible to background noise from cosmic rays and other sources of radiation. That's why they're typically located deep underground, as we discussed earlier, to shield them from these disturbances. And they can only detect charged particles. Neutrinos themselves don't directly produce Cherenkov radiation. It's the charged particles they produce in interactions that do. But despite these limitations, Cherenkov detectors have been incredibly successful in detecting neutrinos and studying their properties. They've played a key role in confirming the existence of neutrino oscillations, a phenomenon that proves neutrinos have mass, and in measuring the mixing angles that govern how they change flavors. Another important type of neutrino detector relies on a phenomenon called scintillation. Certain materials, when struck by a charged particle, emit a flash of light. This flash of light is called scintillation, and it can be detected by photomultiplier tubes, just like in Cherenkov detectors. However, the mechanism is different. Instead of the particle exceeding the speed of light in the medium, the particle excites the atoms or molecules of the scintillator, causing them to emit photons. These photons are then amplified by the photomultiplier tubes, allowing us to detect even very faint signals. The advantage of scintillation detectors is that they can be more sensitive to lower energy neutrinos than Cherenkov detectors. They're also more versatile, as they can be made from a wider range of materials, including liquids and plastics. One example of a scintillation detector is the Camland experiment in Japan. It uses a large tank filled with mineral oil, which acts as both the target material and the scintillator. When a neutrino interacts with the oil, it produces charged particles that excite the oil molecules, causing them to emit light. The light is then detected by photomultiplier tubes located around the tank. Camland is particularly sensitive to antineutrinos produced by nuclear reactors. By measuring the rate of antineutrino interactions, scientists can monitor the output of nuclear reactors and study the properties of antineutrinos. Different scintillator materials have different properties, such as light yield and decay time. The choice of scintillator depends on the specific experiment and the type of neutrino being detected. Scintillation detectors are often used in combination with other detection techniques, such as Cherenkov detectors, to improve their sensitivity and selectivity. For example, some experiments use a combination of a liquid scintillator and a water Cherenkov detector to distinguish between different types of neutrinos and to reject background events. The versatility and sensitivity of scintillation detectors make them an essential tool for neutrino physics, allowing us to probe the mysteries of these elusive particles and to learn more about the fundamental laws of nature. Let's begin with the Homestake Gold Mine in South Dakota. This wasn't just any mine. It was the location of a pivotal experiment led by Raymond Davis Jr. in the 1960s and 70s. Davis was attempting to detect neutrinos, those elusive particles we discussed in the last chapter. The challenge wasn't just their tiny mass, but also their incredibly weak interaction with matter. Most particles zip right through the Earth without a second glance, and neutrinos are masters of this feat. Davis realized that to have any hope of catching them, he needed a massive detector and a lot of shielding from other cosmic rays and background noise. The deep underground location of the Homestake mine provided both. He used a large tank filled with 615 tons of perchloroethylene, a cleaning fluid. This wasn't chosen arbitrarily. The perchloroethylene contained chlorine-37, a rare isotope that, when struck by a neutrino, would transform into argon-37. Argon-37 is radioactive, and Davis could then count the number of argon-37 atoms produced to estimate the number of neutrinos that had interacted. The brilliance of this experiment wasn't just in the sheer scale, but in the ingenious method. Argon-37, being radioactive, decays with a known half-life. Davis and his team meticulously extracted the argon from the perchloroethylene and used a highly sensitive proportional counter to detect decay of any argon-37 atoms. This was incredibly difficult, requiring extreme cleanliness and precise measurements. They expected a certain flux or rate of neutrinos based on theoretical calculations of the nuclear reactions happening in the Sun. These calculations predicted how many neutrinos should reach Earth. However, When Davis analyzed his data, he consistently found only about 1/3 of the expected number. This became known as the solar neutrino problem, and it was a major puzzle for physicists. Was our understanding of the sun wrong? Was there something fundamentally flawed in our understanding of neutrinos themselves? The homestake experiment ran for decades, consistently confirming the deficit. While initially met with skepticism, the results were meticulously verified, and the solar neutrino problem became one of the most important unsolved mysteries in particle physics. It wasn't a matter of faulty equipment. The experiment was carefully calibrated and repeated numerous times. The discrepancy pointed towards a fundamental gap in our knowledge. The prevailing theories suggested that either our models of the sun were drastically incorrect, leading to a lower production of neutrinos, or that something was happening to the neutrinos en route to Earth. This something turned out to be far more interesting than anyone initially imagined. The solution wouldn't come for another 30 years, and it required even more ambitious experiments. Enter Kamiokande, a far more ambitious experiment located deep beneath the mountains in Japan. Built in the late 1980s and early 1990s, Kamiokande used a truly massive detector, a tank containing 50,000 tons of ultra-pure water. Why water? Because water molecules can interact with neutrinos, albeit very weakly. When a neutrino collides with a water molecule, it produces charged particles, electrons or muons, for example. These charged particles travel faster than the speed of light in water. This might sound impossible, but it's permissible because the speed of light is a constant in a vacuum, not in a medium like water. When a charged particle exceeds the speed of light in water, it creates a cone of bluish light known as Cherenkov radiation, a visual signature of the neutrino's interaction. The key to Kamiokande's success was the use of over 3,000 highly sensitive photomultiplier tubes, PMTs, lining the inner surface of the tank. These PMTs are essentially light detectors. When a charged particle creates Cherenkov radiation, the PMTs detect the faint light and amplify the signal. By precisely measuring the amount of light and the pattern of PMTs that are triggered, physicists can reconstruct the energy and direction of the incoming neutrino. This allowed Kamiokande to detect neutrinos from various sources: the sun, supernovae, and even atmospheric cosmic rays. And, crucially, it confirmed the deficit observed by the homestake experiment, but with significantly improved statistics. However, Kamiokande went further than simply confirming the deficit. It revealed something astonishing. The deficit of muon neutrinos from cosmic rays was different from the deficit of electron neutrinos from the sun. This was a crucial clue. It suggested that the problem wasn't simply a misunderstanding of neutrino production rates, but that neutrinos were changing their type as they traveled towards Earth. This phenomenon, now known as neutrino oscillation, implied that neutrinos have mass, something that was previously considered impossible according to the standard model of particle physics. This discovery was groundbreaking and earned a Nobel Prize in Physics in 2015. Let's shift our focus to the Baksan Neutrino Observatory, located in the North Caucasus Mountains of Russia. This observatory, also a large underground detector, utilized a different approach. Instead of water, Baksan employed 3,000 tons of liquid scintillator, a substance that emits light when charged particles pass through it. This allowed for the detection of neutrinos interacting with protons and neutrons within the scintillator. The observatory's location, deep inside a mountain, provided significant shielding from cosmic rays and background noise, similar to the Homestake Mine and Kamiokande. Baksan, while smaller than Kamiokande, played a critical role in confirming the findings of the other experiments. It independently verified the deficit of solar neutrinos and provided further evidence for neutrino oscillations. The observatory's unique design and detector materials allowed it to measure the energy spectrum of the neutrinos with high precision. This data helped to constrain the parameters of the oscillation process and further refine our understanding of neutrino mass and mixing. The combined results from the Homestake experiment, Kamiokande, and Baksan Neutrino Observatory definitively established the phenomenon of neutrino oscillation. This discovery revolutionized our understanding of particle physics, demonstrating that neutrinos have mass, albeit incredibly small, and that the standard model of particle physics was incomplete. It opened up new avenues of research into the fundamental properties of neutrinos and their role in the universe, and continues to be a vibrant area of investigation today. These early experiments weren't just about solving a puzzle. They were about expanding the boundaries of human knowledge and unraveling the mysteries of the cosmos. We've established that neutrinos are created in the sun's core through nuclear fusion. But when scientists started meticulously counting the neutrinos arriving on Earth, a perplexing problem arose. Far fewer were detected than predicted by our best solar models. This discrepancy, known as the solar neutrino problem, wasn't a matter of a small margin of error. The observed rate was only about 1/3 to 1/2 of what was theoretically expected. Now, let's consider what might cause such a deficit. Initially, the thought was that our understanding of the Sun itself was incomplete. Perhaps the temperature in the core was lower than we thought, or maybe the fusion reactions were occurring at a different rate. Extensive work was done to refine our solar models, taking into account the latest observations and theoretical advancements. These efforts did improve the predictions, but a significant discrepancy still remained. Another possibility considered was that something was happening to the neutrinos as they traveled from the Sun to Earth. Perhaps they were being absorbed or scattered by some unknown particles or fields in space. However, these explanations faced challenges, as they required the existence of exotic physics for which there was no other evidence. The initial responses were centered around refining our understanding of the Sun's internal workings. Yet the problem persisted. Scientists delved deeper, exploring alternative fusion pathways and convection models within the Sun. They considered the possibility that the chemical composition of the Sun might be slightly different than previously assumed, which would affect the neutrino production rate. However, even with these improvements, the theoretical predictions still vastly exceeded the observed neutrino flux. It became increasingly clear that the issue wasn't necessarily with our understanding of the Sun itself, but rather with our understanding of the neutrino. The standard model of particle physics, which had successfully predicted the existence and properties of many particles, assumed that neutrinos were massless. If neutrinos did have mass, even a very small mass, it could explain the observed deficit. This is because neutrinos could then oscillate, that is, change between the three known types, as they travel from the Sun to Earth. This oscillation would reduce the number of each type of neutrino detected, effectively hiding some of them from our detectors. Now, let's unpack this neutrino oscillation idea. Remember, there are three flavors of neutrinos: electron neutrinos, muon neutrinos, and tau neutrinos. When neutrinos are created in the Sun's core, they are primarily electron neutrinos. However, as they travel towards Earth, they can spontaneously change into muon neutrinos or tau neutrinos. These other flavors interact much less frequently with matter than electron neutrinos, making them harder to detect. So, by the time the neutrinos reach Earth, a significant fraction of them have oscillated into flavors that our detectors are less sensitive to, resulting in the observed deficit of electron neutrinos. This mixing of neutrino flavors is governed by a set of parameters that describe the probabilities of each type of oscillation. Determining these parameters became a major focus of neutrino physics research, and experiments were designed specifically to measure them. The idea of neutrino oscillation wasn't immediately accepted, however. It required a fundamental revision of the standard model, admitting that neutrinos, contrary to previous assumptions, possess a non-zero, albeit tiny, mass. The simple concept of neutrino oscillation, however, wasn't the whole story. While oscillation could explain a reduction in the number of neutrinos, it didn't fully account for the observed energy spectrum of the detected neutrinos. It turns out that matter itself can influence the oscillation process, a phenomenon known as the Mikheyev-Smirnov-Wolfenstein MSW effect. This effect arises because the interaction of neutrinos with electrons in matter changes the effective mass of the neutrino, altering the oscillation probability. Imagine a neutrino traveling through the Sun's dense core. As it encounters electrons, it experiences a change in its effective mass, which affects how easily it can oscillate. This change is particularly pronounced for electron neutrinos, leading to a resonances condition where the oscillation probability is significantly enhanced. Essentially, the matter in the Sun amplifies the oscillation of electron neutrinos into other flavors. The MSW effect explains why we see fewer electron neutrinos arriving at Earth. As electron neutrinos travel through the Sun's dense core, they are boosted into muon and tau neutrinos. By the time they reach the surface, most of them have already undergone this transformation. This matter enhancement of neutrino oscillation is a crucial component of the solution to the solar neutrino problem. It predicts a specific energy dependence for the detected electron neutrino flux, meaning that neutrinos with certain energies are more likely to have oscillated than others. The MSW effect wasn't merely a theoretical prediction. It provided a framework for understanding the observed energy spectrum of the detected neutrinos and offered a specific signature that could be tested by experiments. Importantly, the strength of the MSW effect depends on the neutrino mass difference, the difference in mass between the different neutrino flavors. Determining this mass difference became a primary goal of neutrino research. The MSW effect wasn't limited to the Sun. It could also occur in the Earth, although the density of matter is much lower. As neutrinos travel through the Earth, they can undergo a similar oscillation process, influenced by the electrons in the Earth's mantle and core. This terrestrial effect is much weaker than the solar effect, but it could still affect the detection of neutrinos from distant sources such as supernovae. Understanding the MSW effect required a precise knowledge of the density profile of the Sun and Earth, as well as the neutrino mass difference. Scientists used sophisticated models and simulations to calculate the expected oscillation probabilities, taking into account the complex interactions between neutrinos and matter. The MSW effect provided a crucial link between particle physics, astrophysics, and geophysics, highlighting the interconnectedness of these different fields of study. The theoretical predictions based on neutrino oscillation and the MSW effect were compelling, but they needed to be confirmed by experimental evidence. Several experiments were designed to detect neutrinos from the Sun and to measure their properties. Early experiments, such as the Homestake experiment, used a large tank of cleaning fluid to detect electron neutrinos produced in the Sun. These experiments confirmed the deficit of electron neutrinos, but they couldn't determine the cause. Later experiments, such as Super Kamiokande in Japan and SNO Submarine Neutrino Observatory in Canada, were much more sophisticated. Super Kamiokande used a huge tank of water surrounded by thousands of photomultiplier tubes to detect Cherenkov radiation. The light emitted when a neutrino interacts with a water molecule, SNO, uniquely used heavy water in which the hydrogen atoms are replaced by deuterium, to allow for the detection of all 3 neutrino flavors. The results from SNO were groundbreaking. They showed that the total number of neutrinos arriving from the Sun, the sum of all 3 flavors, was consistent with the predictions of the standard solar model, which accurately describes the energy production in the Sun. However, the number of electron neutrinos was significantly lower than predicted, confirming that electron neutrinos were oscillating into muon and tau neutrinos. This provided the definitive evidence for neutrino oscillation and the MSW effect. The SNO experiment was able to measure the flux of each neutrino flavor, allowing scientists to determine the parameters governing neutrino oscillation with unprecedented precision. This confirmed the theoretical predictions and provided a complete solution to the solar neutrino problem. The success of SNO and Super Kamiokande marked a triumph for particle physics and astrophysics. The confirmation of neutrino oscillation and the MSW effect has had a profound impact on our understanding of the universe. It showed that neutrinos are not the massless particles that were once thought, but have a tiny non-zero mass. This discovery has implications for cosmology, as neutrinos could contribute to the dark matter content of the universe. It also raises fundamental questions about the nature of mass and the origins of the universe. Ongoing experiments continue to probe the properties of neutrinos with even greater precision, seeking to unravel the mysteries of these elusive particles. The story of the solar neutrino problem is a remarkable example of how scientific inquiry, experimental innovation, and theoretical insight can come together to solve one of the most challenging puzzles in physics and astronomy. Now let's delve into a fascinating puzzle, the muon neutrino deficit. To understand this, we first need to remember how atmospheric neutrinos are created. When cosmic rays, high-energy particles from space, collide with atoms in the Earth's upper atmosphere, they produce a cascade of secondary particles. Among these are neutrinos, and specifically muon neutrinos, are created in abundance. These muon neutrinos should travel towards us, passing through the Earth with minimal interaction. However, when scientists began to meticulously measure the number of muon neutrinos arriving at detectors deep underground, they found something unexpected. Fewer muon neutrinos were detected than predicted by the standard model of particle physics. It wasn't a massive discrepancy, but a consistent and statistically significant one. This wasn't a problem with the detectors themselves. The detectors were carefully calibrated and confirmed to be functioning correctly. The predicted rate was based on well-understood physics, the flux of cosmic rays, the probabilities of different particle interactions, and the expected mean lifetime of a muon. The problem was that the observed rate didn't match the prediction. This difference, this deficit, was the first hint that something wasn't quite right with our understanding of these ghost particles. Now, let's consider why this deficit was so perplexing. The muon neutrino, as you recall, is a slightly heavier cousin of the electron neutrino. Muons themselves are unstable particles, and they decay into electrons and neutrons and other particles with a mean lifetime of about 2.2 microseconds. However, because they are traveling at nearly the speed of light, time dilation comes into play. From our perspective, their lifetime is effectively extended, allowing them to travel quite a distance before decaying. Therefore, the expected number of muon neutrinos reaching a detector depends on both the initial production rate and the muon's survival rate during its journey. Scientists had carefully accounted for this time dilation effect when making their predictions. The implication was that either the initial production of muon neutrinos was lower than expected, or the muons were decaying faster than predicted, or something else entirely was happening. Early attempts to explain the deficit included possibilities like errors in the measurement of the cosmic ray flux, or perhaps a misunderstanding of the atmospheric composition. But these explanations were quickly ruled out by further experiments and data analysis. The discrepancy persisted, growing stronger with each new measurement. This isn't a simple case of needing to refine a few numbers. It suggested a fundamental flaw in our understanding of neutrino behavior. The muon neutrino deficit wasn't just an observational puzzle. It challenged the very foundations of the Standard Model. The Standard Model, for all its success, assumes that neutrinos are massless. If neutrinos were massless, they would travel at the speed of light and wouldn't undergo any changes during their journey. But the deficit suggested that neutrinos were somehow disappearing as they traveled, implying that they were changing into other types of neutrinos. This idea, although radical, provided a potential explanation for the observed discrepancy. Now, this isn't to say that the Standard Model was immediately wrong. It's more accurate to say that it was incomplete. The deficit hinted at the existence of physics beyond the Standard Model, physics that could explain the behavior of these elusive particles. The challenge was to find that physics, to identify the mechanism that was causing the disappearance of the muon neutrinos. It was like finding a missing gear in a complex machine, a gear that was essential for the proper functioning of the entire system. And the next chapter in this story, as we'll see, would involve a remarkable experiment designed to search for that missing gear. The Super Kamiokande detector, located deep beneath the mountains of Japan, was designed to be the ultimate neutrino observatory. It's a massive tank filled with 50,000 tons of ultra-pure water, surrounded by over 11,000 photomultiplier tubes. These tubes are incredibly sensitive detectors of light. When a neutrino interacts with a water molecule, it produces a tiny flash of light which is detected by the photomultiplier tubes. By analyzing the pattern of light, scientists can determine the type of neutrino and its energy. This is an incredibly difficult task, akin to spotting a firefly in a stadium at night. Super Kamiokande wasn't just designed to detect atmospheric neutrinos, it was designed to study them in detail. By measuring the energy and direction of incoming neutrinos, scientists could reconstruct the cascade of particles created by their interactions. This allowed them to determine the type of neutrino that initiated the event and to study its properties. The sheer size of the detector was crucial. A larger detector meant a higher probability of detecting rare events, like neutrino interactions. It was like casting a wider net to catch more fish, and the ultra-pure water was essential to minimize background noise, preventing false signals from interfering with the neutrino detection. The data collected by Super Kamiokande provided a wealth of information about atmospheric neutrinos, and it confirmed the muon neutrino deficit, but it went much further. Super Kamiokande demonstrated that the deficit wasn't the same for all energies of neutrinos. High-energy neutrinos were less affected than low-energy neutrinos. This was a crucial clue. If neutrinos were simply disappearing, the deficit should be the same for all energies. The fact that it varied with energy suggested that something more complex was happening. The detector also provided evidence that the muon neutrinos weren't just disappearing, they were transforming into tau neutrinos, a heavier cousin of the electron and muon neutrinos. This transformation wasn't happening randomly. It followed a specific pattern. The probability of a muon neutrino transforming into a tau neutrino depended on the distance it had traveled. The farther the neutrino traveled, the more likely it was to transform. This distance-dependent transformation was a groundbreaking discovery. It meant that neutrinos had mass. If neutrinos were massless, they wouldn't be able to transform into other types of neutrinos. The transformation process, known as neutrino oscillation, requires neutrinos to have a tiny but non-zero mass. It's like a wave oscillating between different states. The frequency of the oscillation depends on the mass of the neutrino and the distance it has traveled. Super Kamiokande didn't just detect neutrino oscillations. It measured the oscillation parameters, the mass differences between the different types of neutrinos, and the mixing angles that determine the probability of each type of neutrino transforming into another. These parameters provided valuable insights into the fundamental properties of neutrinos and the underlying physics that governs their behavior. It was a paradigm shift in our understanding of these ghost particles. The results from Super Kamiokande were so compelling that they earned the Nobel Prize in Physics in 2004. The concept of neutrino oscillation is fundamental to understanding the evidence for neutrino mass. Imagine a wave. If the wave is perfectly consistent, a single frequency and amplitude, it will travel indefinitely without changing. But if the wave is a superposition of two or more different frequencies, it will interfere with itself, creating a complex pattern of peaks and valleys. The amplitude of the wave will vary over time, oscillating between different values. Neutrino oscillation is analogous to this wave interference. A neutrino isn't a single, well-defined particle. It's a quantum mechanical superposition of different flavor states, electron, muon, and tau. As the neutrino travels, these flavor states interfere with each other, causing the probability of detecting each flavor to oscillate over time. The oscillation frequency depends on the mass differences between the different flavor states. The larger the mass difference, the faster the oscillation. Now, how does this relate to the muon neutrino deficit? The muon neutrinos produced in the atmosphere initially travel as pure muon neutrinos. But as they travel towards us, they oscillate into electron and tau neutrinos. The probability of detecting a muon neutrino decreases over time, while the probabilities of detecting electron and tau neutrinos increase. The observed muon neutrino deficit is simply a result of this oscillation. The muon neutrinos aren't disappearing. They're transforming into other types of neutrinos. The Super Kamiokande detector was able to confirm this by detecting the appearance of electron and tau neutrinos alongside the disappearance of muon neutrinos. The rates of appearance and disappearance were consistent with the predictions of the oscillation theory. Further experiments, like the K2K and mine loss experiments, provided independent confirmation of these results. The discovery of neutrino oscillation has profound implications for our understanding of the universe. It tells us that neutrinos have mass, albeit a very small mass. This challenges the standard model of particle physics, which originally predicted that neutrinos were massless. It also suggests that there may be new physics beyond the standard model that can explain the origin of neutrino mass. Neutrino oscillation also plays a crucial role in cosmology. The abundance of neutrinos in the universe affects the formation of large-scale structures like galaxies and galaxy clusters. Understanding neutrino oscillations is therefore essential for understanding the evolution of the universe. The story of neutrino oscillation is a testament to the power of scientific inquiry. By carefully observing the behavior of these elusive particles, scientists have uncovered a fundamental truth about the nature of reality. Now, let's turn our attention to experiments specifically designed to detect neutrinos produced by nuclear reactors. The first major success story here is CAMLAND. That's the Kamioka liquid scintillator experiment. This experiment, located deep underground in Japan, aimed to detect electron neutrinos from a network of nuclear power plants. The core idea is surprisingly elegant. They used a massive tank filled with a special liquid, a liquid scintillator, which emits flashes of light when a neutrino interacts with it. Think of it like a very sensitive light bulb triggered by the ghostly touch of a neutrino. The deep underground location is critical. It shields the detector from cosmic rays and other background noise that could mimic a neutrino signal. This allows them to really isolate the signals they're looking for. CAMLAND wasn't just trying to detect any neutrinos, it was specifically looking for evidence of neutrino oscillations, that is, the change in flavor we've been discussing. The reactors produce a huge number of electron neutrinos. If these neutrinos oscillate into muon or tau neutrinos before reaching the detector, we'd see fewer electron neutrinos than expected. And that's exactly what they found. The results, published in 2002, provided strong evidence for neutrinos possess mass. It was a landmark moment in particle physics. The beauty of CAMLAND lies in its simplicity and the sheer scale of the detector. The liquid scintillator acted as both the target material and the detection medium. When a neutrino collided with a proton or neutron in the scintillator, it produced charged particles. These particles then travel through the liquid, creating a cone of light, a Cherenkov ring, similar to what we discussed earlier, though different in detail. By analyzing the shape and intensity of these light cones, the scientists could determine the energy and type of the interacting neutrino. This allowed them to not only detect the neutrinos, but also to study their properties. One particularly crucial aspect of the experiment was its ability to precisely measure the fluxes, the number of neutrinos passing through a given area per unit time. This is essential for comparing the expected number of electron neutrinos from the reactors with the actual number detected. Any discrepancy would be a telltale sign of neutrino oscillations. The initial results were promising, but statistical significance requires a lot of data. Over several years, CAMLAND accumulated enough data to convincingly demonstrate that the observed deficit of electron neutrinos could not be explained by anything other than neutrino oscillations. This was a major step forward in our understanding of these elusive particles. CAMLAND's success wasn't without its challenges. One major hurdle was distinguishing genuine neutrino events from background noise. Cosmic rays, radioactive decay within the detector materials, and even environmental radioactivity can all produce signals that mimic those of neutrinos. To overcome this, the scientists employed a variety of techniques, including careful shielding, data analysis, and sophisticated statistical methods. They also used multiple layers of detection to help identify and reject background events. For instance, they used an outer layer of water to absorb most of the cosmic rays before they could reach the scintillator. They also carefully calibrated the detector to ensure that it was responding accurately to different types of radiation. The data analysis was particularly complex, requiring sophisticated algorithms to sift through the vast amount of information and identify genuine neutrino signals. It was a truly collaborative effort, involving scientists and engineers from around the world. Camland paved the way for future experiments and solidified our understanding of neutrino oscillations. It demonstrated the power of large-scale underground detectors and the importance of careful data analysis in the search for elusive particles. Following the success of Camland, other experiments were designed to further refine our understanding of neutrino oscillations, specifically focusing on the parameters that govern the process. One such experiment is Double Choose, located in France. The primary goal of Double Choose was to precisely measure the mixing angle θ13, which governs the probability of muon neutrinos oscillating into electron neutrinos. This angle was expected to be very small, making it extremely difficult to measure. The experiment utilized two identical detectors located near a nuclear power plant. Having two detectors allows for a more robust measurement and helps to reduce systematic uncertainties. The detectors are relatively compact compared to Camland, but they are designed to be highly sensitive to electron neutrinos. They utilize a similar principle to Camland, using a liquid scintillator to detect the light produced when a neutrino interacts with the detector material. However, the design of the detectors and the analysis techniques are optimized for measuring the small signal expected from θ13. A crucial aspect of the Double Choose experiment is its location near a nuclear power plant with a relatively compact reactor core. This allows for a high flux of antineutrinos, increasing the probability of detecting a signal. However, it also means that the experiment is subject to a high level of background noise. To mitigate this, the detectors are shielded by layers of concrete, lead, and other materials. They also utilize sophisticated data analysis techniques to distinguish genuine neutrino signals from background events. One of the key challenges facing the Double Choose experiment was the need to accurately model the energy spectrum of the antineutrinos produced by the reactor. This requires a detailed understanding of the nuclear fission process and the decay of the fission products. The scientists collaborated with nuclear physicists to develop accurate models of the reactor antineutrino spectrum. They also performed careful calibrations of the detectors to ensure that they were responding accurately to different energies. In 2012, the Double Choose collaboration announced that they had detected a non-zero value for θ13, providing strong evidence that this mixing angle is not zero. This discovery was a major breakthrough in neutrino physics, as it opened up new possibilities for studying the properties of these elusive particles. A non-zero θ13 also has implications for the search for CP violation in neutrinos, which could help explain the matter-antimatter asymmetry in the universe. The Double Choose experiment continues to collect data, refining its measurements of θ13 and searching for other subtle effects that could reveal new physics. It has paved the way for future experiments, such as T2K in Japan and Dune in the United States, which aim to make even more precise measurements of neutrino properties and explore the full potential of these enigmatic particles. The success of Double Choose highlights the importance of international collaboration and the power of careful experimentation in unraveling the mysteries of the universe. Concurrent with double choose, another major experiment, the Daya-Bay collaboration was also working to measure θ13. Located in China, Daya-Bay employed a similar approach to double choose, utilizing multiple detectors near a nuclear power plant. However, Daya-Bay differed in one crucial aspect. It used 8 identical detectors, divided into 2 experimental sites. This configuration provided even greater statistical power and allowed for a more robust measurement of θ13. The detectors at Daya-Bay were also designed to be highly sensitive to electron antineutrinos, which are produced by the fission of uranium and plutonium in the reactor core. The experiment utilized a liquid scintillator detector, similar to those used in Camland and double choose. However, the Daya-Bay detectors were larger and more sophisticated, allowing for a more precise measurement of the antineutrino energy spectrum. The Daya-Bay collaboration also placed significant emphasis on reducing systematic uncertainties. They carefully calibrated the detectors and developed sophisticated models of the reactor antineutrino spectrum. They also performed extensive background measurements to ensure that they could accurately identify genuine neutrino signals. The experiment benefited from the expertise of a large international collaboration involving scientists from China, the United States, and other countries. The collaboration worked tirelessly to analyze the data and interpret the results. In 2012, the Daya-Bay collaboration announced that they had measured a non-zero value for θ13, confirming the results obtained by double choose. The Daya-Bay measurement was particularly precise, providing a strong constraint on the value of θ13. The combined results from double choose and Daya-Bay have revolutionized our understanding of neutrino mixing. The discovery of a non-zero θ13 has opened up new avenues for research in neutrino physics. It has also paved the way for future experiments that aim to study the properties of neutrinos in even greater detail. The Daya-Bay experiment continues to collect data, refining its measurements of θ13 and searching for other subtle effects that could reveal new physics. It serves as a shining example of international collaboration and the power of scientific inquiry. The success of these experiments has solidified our understanding of the fundamental building blocks of the universe and has opened up new possibilities for exploring the mysteries of the cosmos. Now let's turn our attention to a rather intriguing puzzle, dark matter. We know it's there, influencing galaxies, but what is it? One of the earliest ideas revolved around its temperature. This isn't temperature in the conventional sense, but rather a measure of how fast these dark matter particles were moving in the early universe. Hot dark matter would be composed of particles moving at relativistic speeds, close to the speed of light. Imagine them whizzing around, blurring the initial density fluctuations in the early universe. These fluctuations are crucial. They're the seeds from which galaxies eventually form. If the particles were too hot, they'd smooth out these fluctuations, preventing galaxies from forming in the way we observe them. Think of it like shaking a container of marbles. If you shake it violently, the marbles will distribute evenly. Gentle shaking leads to clumps. Hot dark matter, according to simulations, wouldn't produce enough of the small-scale structures, the smaller galaxies and clusters that we see today. This led scientists to propose cold dark matter. These particles would be much slower, non-relativistic, meaning they moved at a fraction of the speed of light. Imagine them as gently drifting snowflakes rather than speeding bullets. Because they were slower, they could clump together more easily under the influence of gravity. This allowed the early density fluctuations to grow undisturbed, eventually forming the large-scale structures we see today. Galaxies, clusters of galaxies, and the vast cosmic web. Cold dark matter predicts a hierarchical structure formation, smaller structures forming first, then merging to create larger ones. This aligns remarkably well with observations. However, even with cold dark matter, there are some discrepancies, particularly on the smaller scales, leading us to consider more complex models and, ultimately, to explore the potential role of neutrinos. The standard lambda CDM model, lambda representing dark energy and CDM standing for cold dark matter, is currently the most successful model for describing the evolution of the universe. However, it's not perfect. There are still some puzzles, such as the missing satellites problem. The model predicts more small satellite galaxies around larger galaxies like our Milky Way than we actually observe. And, as we'll discuss, neutrinos might offer a fascinating bridge between hot and cold dark matter, potentially explaining some of these discrepancies. It's important to remember that science isn't about finding the answer, but about refining our understanding and exploring new possibilities. The story of dark matter and the role of neutrinos within it is still being written. Now, let's introduce the idea of sterile neutrinos. We already know about the three active neutrinos, the electron, muon, and tau neutrino, which interact through the weak force. Sterile neutrinos, however, wouldn't interact through any of the fundamental forces except gravity. This makes them incredibly difficult to detect. The concept arose from anomalies observed in neutrino oscillation experiments. These experiments showed that neutrinos change flavor. That is, they oscillate between electron, muon, and tau types, and the observed oscillation rates didn't quite match the predictions based on only 3 active neutrinos. A fourth, sterile neutrino, could potentially explain these discrepancies. It's like adding a missing piece to a puzzle. The mass of this sterile neutrino is crucial. If it's relatively light, say a few keV electron volts, it could also contribute to dark matter. Unlike the hot, dark matter particles we discussed earlier, these keV scale sterile neutrinos wouldn't be moving at relativistic speeds. They'd be warm, dark matter, somewhere between hot and cold. This could help resolve some of the discrepancies in the standard cold dark matter model, like the missing satellites problem. The idea is that these warm dark matter particles would have slightly more free streaming in cold dark matter, suppressing the formation of the very smallest structures. However, detecting sterile neutrinos is incredibly challenging. Because they interact so weakly, they're almost invisible to our detectors. We can't directly see them. Instead, scientists are looking for indirect evidence. One possibility is to search for X-ray signatures. Sterile neutrinos could decay into ordinary neutrinos and photons light particles, and these photons could be detected as a faint X-ray glow. Another approach involves looking for anomalies in neutrino oscillation experiments, or searching for effects on the cosmic microwave background, the afterglow of the Big Bang. It's like searching for a needle in a haystack, but the potential reward, understanding the nature of dark matter and the fundamental properties of neutrinos, is immense. So, how are scientists actually searching for these elusive sterile neutrinos? Several experiments are dedicated to this task, employing different techniques. One prominent approach involves looking for sterile neutrino oscillations at short baseline neutrino sources. These sources like nuclear reactors or spallation sources, produce intense beams of neutrinos. By carefully measuring the number of neutrinos detected at different distances from the source, scientists can search for evidence of oscillations into sterile neutrinos. The key is to look for a deficit in the number of active neutrinos, which would indicate that some have disappeared into the sterile sector. Another avenue of research involves searching for the X-ray signature we discussed earlier. This is particularly challenging because the expected X-ray flux is incredibly faint and can be easily masked by background noise. Experiments like the micro-immersed spheres MISS experiment are designed to detect these faint X-rays using highly sensitive detectors and sophisticated data analysis techniques. These experiments require extremely low background environments, often located deep underground, to shield them from cosmic rays. The search for sterile neutrinos is ongoing, and the results are still inconclusive. While some experiments have hinted at anomalies that could be interpreted as evidence for sterile neutrinos, these results are not yet statistically significant. More data and more sophisticated analysis are needed to confirm or refute their existence. It's a challenging and exciting field of research, with the potential to revolutionize our understanding of neutrinos, dark matter, and the fundamental laws of the universe. The quest to unravel the mysteries of the cosmos continues, driven by the curiosity and dedication of scientists around the world. Let's begin with the very early universe, a period dominated by immense heat and density. We're talking fractions of a second after the Big Bang. In this extreme environment, it wasn't possible for atoms, as we know them, to exist. Instead, we had a primordial soup of fundamental particles, quarks, leptons, including now ghostly neutrinos, and photons. As the universe expanded and cooled, things began to change. This cooling allowed protons and neutrons to form, and these, in turn, started to combine. This process is called Big Bang nucleosynthesis, or BBN. It's essentially the first instance of element creation in the universe. It's vital to understand that this wasn't like a star forging elements. This was a direct result of the universe's initial conditions and expansion rate. The relative abundance of light element hydrogen, helium, and lithium we observe today is a direct consequence of the conditions during BBN. Now, how do neutrinos fit into all this? Well, the rate at which protons and neutrons combine to form heavier nuclei is incredibly sensitive to the number of neutrinos present in the early universe. Neutrinos, despite being notoriously difficult to detect, were incredibly abundant back then. They played a crucial role in determining the precise ratio of neutrons to protons. More neutrinos meant a faster conversion of neutrons into protons, which affected the final abundance of helium. If the number of neutrino flavors electron, muon, and tau had been different, the universe would have a drastically different composition. The amount of helium we observe today provides a strong constraint on the number of neutrino flavors that were present during BBN. It's like a cosmic detective story, using the abundance of elements to deduce properties of these elusive particles. The precision with which BBN predictions match the observed abundances of light elements is truly remarkable. This provides strong evidence for the Big Bang theory and also helps us constrain cosmological parameters like the density of the universe. Any significant deviation between predictions and observations would suggest flaws in our understanding of either particle physics or cosmology. It's a beautifully interconnected picture. Essentially, the abundance of helium acts as a measuring stick, allowing us to probe the conditions of the early universe and learn about the properties of neutrinos. We can calculate what the universe should look like, given our understanding of neutrinos, and compare it to what we observe. This is powerful validation. The fact that they align is a testament to the success of the standard cosmological model. Now, let's move forward in time, some 380,000 years after the Big Bang. The universe had cooled enough for electrons to combine with nuclei, forming neutral atoms. This was a momentous event because it allowed photons, light particles, to travel freely through space without constantly scattering off free electrons. Before this time, the universe was opaque, like a dense fog. After this recombination event, the universe became transparent. The photons released at that moment are what we observe today as the cosmic microwave background, or CMB. Think of it as the afterglow of the Big Bang, a faint echo from the early universe. It's the oldest light we can possibly detect. The CMB isn't perfectly uniform, though. There are tiny temperature fluctuations, or anisotropies, in the CMB. These fluctuations represent seeds of all the structure we see in the universe today. Galaxies, clusters of galaxies, and the vast cosmic web. The size and distribution of these fluctuations provide a wealth of information about the early universe, including its age, geometry, and composition. And, crucially, they can tell us about the role of neutrinos. The presence of massive neutrinos, even though they don't interact strongly with light, does affect the CMB. Massive neutrinos suppress the growth of structure on small scales, leaving a subtle imprint on the CMB's pattern. By carefully analyzing the CMB, cosmologists can constrain the mass of neutrinos. The more massive the neutrinos, the more suppressed the growth of small-scale structures, and the more noticeable the effect on the CMB. Current observations from missions like Planck tell us that the total mass of all three neutrino flavors must be less than about 0.12 electron volts. This is a relatively small amount, but it's still enough to have a measurable effect on the universe. The CMB, therefore, serves as a powerful probe of neutrino properties, complementing the information we get from terrestrial experiments. It's a beautiful example of how different areas of physics can come together to paint a more complete picture of the cosmos. Let's now consider the large-scale structure of the universe, the distribution of galaxies and clusters of galaxies on the larger scales. This structure isn't random. It's organized into a vast cosmic web, with dense filaments of galaxies surrounding large, empty voids. This web forms through gravitational instability. The tiny density fluctuations in the early universe, which we saw imprinted on the CMB, grew over time due to gravity. Regions with slightly higher density attracted more matter, becoming denser still, and so on. This process eventually led to the formation of the structures we observe today. Now, how do neutrinos affect this structure formation? Well, neutrinos are what's known as hot dark matter, or might cold dark matter, which is thought to be composed of weakly interacting massive particles, or WIMPs. Neutrinos move at close to the speed of light. This high velocity means they tend to wash out small-scale structures. In the early universe, the free streaming of neutrinos smoothed out density fluctuations on small scales, suppressing the formation of small galaxies. Simulations that don't include the effects of neutrinos predict more small galaxies than we actually observe, which is a problem. Therefore, the observed distribution of galaxies provides another constraint on the mass of neutrinos. The more massive the neutrinos, the more suppression of small-scale structures, and the better the agreement between simulations and observations. Current observations suggest that neutrinos make up a relatively small fraction of the total dark matter in the universe, but they still play a crucial role in shaping the large-scale structure we see today. They act as a kind of smoothing agent, preventing the universe from becoming overly clustered. It's a subtle but important effect, and it highlights the interconnectedness of particle physics and cosmology. By studying the distribution of galaxies, we can learn about the properties of these elusive particles and vice versa. DUNE, or the Deep Underground Neutrino Experiment, represents a truly ambitious step forward in neutrino physics. It's not just one detector, but a complex system designed to observe neutrinos over a remarkable distance. Imagine a beam of neutrinos created at Fermilab in Illinois, traveling nearly 800 miles to be detected by massive argon-filled detectors located deep underground in South Dakota, at the Sanford Underground Research Facility. This isn't a direct line-of-sight setup. The Earth shields these detectors from most other cosmic rays and background noise, allowing for incredibly precise measurements. The sheer scale is breathtaking. The detectors will be far larger and more sensitive than anything we've previously deployed. DUNE's primary goal is to unravel several key mysteries. We've established that neutrinos oscillate, changing flavors between electron, muon, and tau neutrinos. But the parameters governing these oscillations, particularly the CP violating phase, remain poorly constrained. Understanding this phase is crucial to explain the matter-to-matter asymmetry in the universe, why there's so much more matter than antimatter. The choice of liquid argon as the detection medium is deliberate. When a neutrino interacts with an argon nucleus, it produces a cascade of particles, electrons, muons, and others. These particles leave ionization trails within the argon, which are then detected by sophisticated sensors. The density of the argon is key. More massive detectors have larger target volumes, increasing the probability of neutrino interactions. But it's not simply about size. Argon provides excellent resolution, meaning we can precisely reconstruct the paths of these particles and determine the type of neutrino that caused the interaction. DUNE's detectors will be capable of distinguishing between electron and muon neutrinos with remarkable accuracy. This is vital for measuring the CP violating phase, as this phase affects the oscillation probabilities for different neutrino flavors. The experiment also aims to detect supernova neutrinos, providing valuable insights into the collapse of massive stars. The location of DUNE at the Sanford Underground Research Facility is no accident. Being deep underground shields the detectors from cosmic rays and other background noise. The facility is a former gold mine, providing a vast, cavernous space for the detectors. Constructing these detectors underground is a monumental undertaking. It requires careful planning, precise engineering, and a dedicated team of scientists and engineers. The detectors are being assembled in layers, with each layer carefully tested and calibrated. The entire process is expected to take several years. Beyond CP violation and supernova neutrinos, DUNE also has the potential to detect proton decay. Proton decay is a theoretical process predicted by some extensions to the standard model of particle physics. If proton decay occurs, it would be a profound discovery, revolutionizing our understanding of matter and the universe. DUNE is truly a flagship experiment for the next generation of neutrino physics. Now let's journey to Japan and explore Hyper Kamiokande. This detector, like its predecessor Super Kamiokande, is based on the principle of detecting Cherenkov radiation. When a neutrino interacts with water molecules, it can produce charged particles traveling faster than the speed of light in water. This creates a cone of blue light, Cherenkov radiation, which is then detected by an array of photomultiplier tubes lining the walls of the detector. Hyperkamiokande is significantly larger than Superkamiokande, with a volume of 370,000 tons of ultra-pure water. This increased size translates to a higher event rate, allowing for more precise measurements. The detector is located deep underground in the Kamioka mine, shielding it from cosmic rays and background noise. The primary goal of Hyperkamiokande is to make a definitive measurement of CP violation in the lepton sector. The increased sensitivity of Hyperkamiokande will allow scientists to probe the parameters governing neutrino oscillations with unprecedented precision. By measuring the CP violating phase, they can determine whether neutrinos and antineutrinos behave differently. This is crucial for understanding the matter-antimatter asymmetry in the universe. In addition to CP violation, Hyperkamiokande will also be sensitive to supernova neutrinos. It will be able to detect a large number of neutrinos from a nearby supernova explosion, providing valuable insights into the processes that occur during the collapse of a massive star. The detector is also designed to search for proton decay, although its sensitivity to proton decay will be lower than that of Dune. Hyperkamiokande represents a continuation of the successful Superkamiokande experiment, building on its legacy and pushing the boundaries of neutrino physics. The location of Hyperkamiokande in the Kamioka mine is ideal. The mine provides a stable and shielded environment for the detector. The surrounding mountains provide additional shielding from cosmic rays. The experiment is a collaborative effort involving scientists from around the world. The construction of the detector is a complex undertaking that requires careful planning and execution. The first data from Hyperkamiokande is expected to be collected in the late 2020s. This will mark a new era in neutrino physics, allowing scientists to probe the fundamental properties of neutrinos with unprecedented precision. Hyperkamiokande is poised to make groundbreaking discoveries that will revolutionize our understanding of the universe. Finally, let's travel to China and explore NU, the Jiangmen Underground Neutrino Observatory. NU employs a different detection technique than Dune or Hyperkamiokande. It utilizes a large liquid scintillator detector containing around 20 kilotons of acrylic to detect inverse beta decay. This process occurs when an antineutrino interacts with a proton, producing a positron and a neutron. The positron annihilates with an electron, emitting photons, while the neutron is captured by the scintillator, also emitting photons. These photons are then detected by an array of photomultiplier tubes. Juno's primary goal is to determine the neutrino mass ordering, whether the neutrino mass hierarchy is normal or inverted. This is a fundamental question in neutrino physics that has remained unanswered for decades. Juno's large size and high resolution allow it to precisely measure the energy spectrum of neutrinos. This is crucial for determining the neutrino mass ordering. The detector is located deep underground in the Kaiping County, Guangdong Province, shielding it from cosmic rays and background noise. In addition to determining the neutrino mass ordering, Juno will also be sensitive to supernova neutrinos and the Earth's neutrino flux. The Earth's neutrino flux is produced by the decay of radioactive isotopes within the Earth's interior. By measuring this flux, scientists can learn more about the composition and structure of the Earth. Juno represents a significant contribution to the field of neutrino physics, offering a unique perspective on these elusive particles. The construction of Ryuno involved a massive international collaboration. The detector is a testament to the power of scientific cooperation. The experiment is expected to begin collecting data in the late 2020s. Neutrino is poised to make groundbreaking discoveries that will revolutionize our understanding of neutrinos and the universe. These three experiments, Dern, Hypercamia-Candy, and Journo, represent the future of neutrino physics, each offering a unique approach to unraveling the mysteries of these fundamental particles. Together, they will paint a more complete picture of the neutrino universe. We've journeyed through the fascinating world of particles, haven't we? From the robust building blocks of matter to the fleeting carriers of force. But there's a certain class of particle that has consistently defied easy categorization, the neutrino. For decades they were considered almost ghostly, barely interacting with anything. But that seeming indifference is precisely what makes them uniquely capable of carrying information from the deepest, most inaccessible corners of the universe. Think of it this way. Most particles are like trying to send a message through a crowded marketplace. Lots of collisions, lots of getting lost. Neutrinos, they're like sending a message through empty space. They can travel for light years without being disturbed. This isn't a limitation, it's their superpower. This ability to penetrate matter with ease allows them to act as direct messengers from processes hidden from our conventional observational tools. It's like having a secret window into realms previously obscured. So, what kind of secrets are these elusive particles carrying? Many of them originate from the core of the Sun, a process called fusion. Billions of neutrinos are produced every second, streaming outwards in all directions. Detecting these solar neutrinos was a monumental achievement, confirming our understanding of stellar energy production. But the Sun is just the beginning. Supernovae, the explosive deaths of massive stars, also release enormous numbers of neutrinos. These supernova neutrinos can provide crucial insight into the physics of these cataclysmic events, telling us about the conditions in the star's core before and during the explosion. These aren't just numbers or measurements, they are snapshots of some of the most energetic, violent and fundamental processes in the universe. And because neutrinos interact so weakly, they escape the dense debris of the supernova, carrying information that light simply can't. Think of them as the ultimate witnesses to cosmic events. But the really exciting part is that neutrinos aren't just telling us about the past. They're also offering clues about some of the biggest mysteries in modern physics. Remember the problem of matter-antimatter asymmetry? The universe seems to be overwhelmingly dominated by matter, but our theories predict that equal amounts of matter and antimatter should have been created in the Big Bang. Neutrinos might hold the key to resolving this discrepancy. Certain neutrino properties, like their mass and mixing patterns, could provide a subtle asymmetry that favored matter over antimatter in the early universe. This isn't some abstract theoretical exercise. Understanding this asymmetry is crucial for understanding why we, and everything around us, even exist. It's a fundamental question about the nature of reality itself, and neutrinos are helping us inch closer to an answer. Let's move beyond just understanding the fundamental laws of physics and consider how neutrino astronomy is reshaping our view of the cosmos. Traditional astronomy relies on observing elect radiation, light, radio waves, X-rays, and so on. But these signals can be blocked by dust and gas, obscuring our view of certain regions of space. Neutrinos, however, can pass right through these obstacles. This opens up a new window into the universe, allowing us to observe objects and events that are hidden from conventional telescopes. Imagine being able to see the core of a collapsing star or the inner workings of an active galactic nucleus. That's the promise of neutrino astronomy. One of the most exciting applications of neutrino astronomy is the study of extreme astrophysical objects like black holes and neutron stars. These objects are often surrounded by dense clouds of gas and dust, making them difficult to observe with conventional telescopes. However, neutrinos produced in the vicinity of these objects can escape relatively unimpeded, providing a unique way to probe their inner workings. For instance, the detection of neutrinos from a supernova remnant could provide crucial insights into the physics of core collapse supernovae, helping us understand how these massive stars explode and seed the universe with heavy elements. It's like having a secret code that allows us to decipher the hidden language of the cosmos. Furthermore, the study of high-energy cosmic rays is also benefiting from neutrino astronomy. Cosmic rays are energetic particles that travel through space, bombarding the Earth from all directions. However, their origin is still a mystery. When cosmic rays collide with interstellar gas, they produce secondary particles, including neutrinos. By detecting these secondary neutrinos, we can trace the path of the cosmic rays back to their sources, potentially revealing the sites of particle acceleration in the universe. This is a complex undertaking, requiring sophisticated detectors and advanced data analysis techniques. But the potential rewards are immense. It could unlock some of the biggest mysteries in astrophysics, revealing the secrets of the most energetic phenomena in the universe. So, what does the future hold for neutrino physics? The next generation of neutrino detectors are poised to revolutionize our understanding of these elusive particles. These detectors will be significantly larger and more sensitive than their predecessors, allowing us to detect a much greater number of neutrinos and probe their properties with unprecedented precision. One of the key goals is to determine the neutrino mass hierarchy, the order of the masses of the three different types of neutrinos. This is a fundamental question that has implications for our understanding of the universe and the laws of physics. Furthermore, experiments are underway to search for sterile neutrinos, hypothetical particles that do not interact with matter through the weak force. If sterile neutrinos exist, they could explain some of the anomalies observed in neutrino experiments and provide a new window into the dark sector of the universe. The search for sterile neutrinos is a challenging undertaking, requiring incredibly sensitive detectors and sophisticated data analysis techniques. However, the potential rewards are immense, as it could revolutionize our understanding of the fundamental building blocks of matter. These experiments, often located deep underground to shield them from cosmic rays, represent the forefront of particle physics research. Ultimately, the future of neutrino physics is bright. With continued investment in research and development, we can unlock the secrets of these elusive particles and gain a deeper understanding of the universe. Neutrinos are not just particles. They are messengers from the cosmos, carrying information about the most extreme and mysterious phenomena in the universe. By listening to these messengers, we can unravel the secrets of the cosmos and gain a deeper appreciation for the beauty and complexity of the universe. The journey is just beginning, and the potential for discovery is limitless.